Where is new arc? What will you say?
Recording in progress.
Where is new arc? Left, right, something. How will you say? Go to right, take right. Swim 10,000 kilometers. And if you survive, then you reach East Coast of United States, something like that. But you know that it does not make sense. In a scientific language, we need some scientific notation. So, like on our planet, we have something called longitude and altitude. Latitude and longitude. Fine. So you can uniquely determine the position of any place on Earth by just giving two numbers, latitude and longitude. So this information of coordinates, has anyone taught you? Who? Oh, there are some lectures on it. So they taught you different coordinate systems and all. I was asking someone who came to meet me like yesterday or day for a study. Someone I asked that whether coordinate system etc. has been covered. They studied all the four coordinate systems and all. Equatorial, ecliptic, galactic. I did not bring my laptop, otherwise I had everything, like I could be something different also. But now I have only two choices. Either you want to study Dwrafs or you want to study coordinate system. So let us anyway. So you are more familiar with equatorial coordinate system. Okay, so I will tell you more about three other types of coordinate system. At least there's something new. Then I will tell you something more other steps. We have to finish 1 hour. Na? Okay. So you understood the importance of coordinate systems to identify the location of any astrophysical object in the sky. So before that, let's start something. This branch of astronomy is also called in a general sense, it's called astrometry. Fine? It's more like measurements. So what is this? This is the field of astronomy dedicated to determination of fundamental reference systems, distance and angular separation between celestial objects, accurate measurements of time, and corrections due to precision in notation. Collectively, this is called astrometry. This also requires accurate measurement of time, angular separation between two astrophysical objects. The question is, how will you measure them? You cannot just say that, okay, like 2 fingers. You have to identify, give to some number. Okay, who will tell me what is nutation?
From precision that there is some.
Good. Anyone else? No one else. Fine. So you know there are 3 types of motion. One is you are Earth. So Earth is one thing. Earth is rotating like this. One thing, Earth is rotating on its own axis. Day-night happened because of this motion. This we are calling as rotation. Fine. Along with that, Earth is also rotating around some axis. Okay. This motion is called precision. Lattu suna hai? Lattu. That you just throw it. You see, it rotates on its own axis, but it precesses also. Okay. Fine. The nutation is this little jiggling. You see, there are 3 motions. Everything is happening. Got it? What is nutation? You understood? Okay. When you go back, you throw them everything. Let's see. So that's what we do. Maybe. Fine. You understood rotation, precision, and nutation. So see, whenever we do any scientific measurement, we have to take care of all these factors. Okay. Astrometry deals with the arcs, angles, triangles on the surface of the celestial sphere. So what? And this is different from Euclidean geometry. Euclidean geometry is our planar geometry, where the sum of angle sum of angles of a triangle is 180 degrees. But on spherical astronomy, this may not be. Like you draw a triangle on the surface of a sphere. You understood? The angle may not be. First of all, it may not be like the plane angle you are expecting. That will not. Got it? So for the rest of the lesson, we will assume it's like a hopeful universe, whatever. It's like a perfect sphere. Okay. So this astrometry, what we are, this is also called spherical astronomy. And in this spherical astronomy, we consider celestial objects as dots on the surface of a sphere of unit radius. So here we presume that we are at the center of this sphere of a unit radius, and all celestial bodies are lying at the surface. Clear? Got the idea? Observer is at the center of that sphere, and all other astrophysical bodies are lying on the surface. Fine, this is the assumption we will just keep in mind. So let us start with simple thing. You know, this is a sphere. You can only see a circle, but assume it's a three dimension. You cut this sphere with some plane somewhere. So you will see the intersection of this plane with the sphere will be a circle. Okay? Fine. But if this plane is passing through the center, so this intersected circle is called the great circle. Small circle, great circle. So great circle is the case when the plane is passing through the center. Then whatever the circle will be like intersect. This is called the great circle. And if the plane is passing through anywhere else, the intersected circle will be called small circle. This I already told you. Fine. So you know that the shortest distance between 2 points on a sphere is an arc on the great circle. In other words, if I ask you that this is 1 point and this is another point, what is the distance? What is the shortest distance between these 2 points? You can understand. First of all, you are not on a plane, so you cannot draw a straight line. But you can draw any line, like this, like this, like this, this, anything you can draw. So one of the line will be shortest. Which line will be shortest? The line that will be shortest will be along that great circle, something like this. You understood? Like cut it this way. Okay. If you sometimes use a search in Google, if you see the trajectory followed by Air India plane when it goes to United States, say from New Delhi. Okay. So if you see the world's map, it will look like New York is somewhere here, New Delhi is somewhere here. You can directly draw a straight line. But if you see the path followed by Air India plane, it goes something like this. It goes via Iceland, Greenland, Afghanistan, Ukraine, Russia, Iceland, Greenland, and then via Canada, it enters United States. As in that. As in big icebergs, etc., floating on the sea. So why it goes that way? Because basically, though it looks like it is going following a longer path, but that is the shortest path. That it goes along the great circle. And the straight that we see, if you just see that not only for US, we say Air India, New York to Delhi flight, go for any flight, they always try to follow the arc along the great circle because that is the shortest distance. And this derivation you can do. It's a simple geometrical derivation. I will leave you to do it. Search in Google, you'll find it. Fine. Got the idea? Now, if I ask you what is it, you cannot just say no, that is. Okay? So there should be a definition of pole also. So pole, what is the pole? Pole, first of all, pole of a great circle. So for different great circles, pole could be different. You have one great circle. Suppose you have a plane. You have say some cardboard sheet. That is I'm telling you, a plane. You have a sphere. Okay. If I tell you, you first of all what you do? You draw one horizontal plane passing through the diameter. Like what you are seeing here is this. You are seeing this. Okay. Now you draw. So this is a great circle, correct? Now you draw two great circles perpendicular to this great circle. Okay, you can see this angle 90 degrees. Huh? Okay, so wherever these great circles intersect, that point is I'm calling it. Okay, so poles of a great circle are intersections of the diameter of the sphere. So see, this is also another great circle. You see, this one goes down and it comes up like this, and then another great circle like this, and wherever they are intersecting, we are calling that again. The condition is that these two great circles should be perpendicular to the horizontal great circle. That's all. Fine. And you understand this they will intersect somewhere here also, somewhere at bottom. Not only on top, they will intersect at the bottom also. No? So these two positions, both of them are called pole. And they are diametrically opposite points. Okay? Here. Now one more thing, see, I'm just telling you small terminology. That's what we usually use. The angle generated by the intersection between two great circle arcs is the angle between their planes. You have a two great circles. So basically you have two planes. One is like this, one is like this. You can see this pink color and cyan color. These are basically planes. Fine. So this angle in between, okay, is called spherical angle. Just a minute. Fine. Now the another definition is called zenith. What is zenith? Suppose you are the observer. Zenith is the point directly overhead of you. So you see, you might have read about zenith. Word is being used in like common day life also. That you have reached the zenith of your career. Peak. That means like you have reached. Right? So zenith is the point directly overhead the observer. Here I am presuming that observer is at the center of that sphere. Okay, this already understood. Now there is something called antipod. What is this antipod? Antipod is a point diametrically opposite to another on the surface. In other words, if I say Nadir, Nadir is the antipod of Zenith. South Pole is the antipod of North Pole. आप समझ में आ गया? Everybody understood. So it's just a term name. Antipod means antipod of something. Something could be any point. So suppose if my point is North Pole, I'm asking what is the antipod of North Pole? South Pole. What is the antipod of Zenith? Nadir. Okay? Easy. What will be the antipod of Nadir? Good. Fine? Understood? Then there is something called meridian. Great circle passing through the celestial poles as well as zenith and nadir of an observer's location. Suppose, just try to understand first. Suppose the observer is here, okay, and I am telling my celestial north pole is this point, somewhere there. See, that's what now. Zenith is this point, but my north pole could be somewhere over there. It depends on my axis of my rotation. That's the axis of rotation of that sphere, isn't it? Okay, North Pole is there, Zenith is here. South Pole will be somewhere over there. Northern will be somewhere low, down. Fine. So meridian is the great circle passing through pole as well as zenith. Now you have constraint. So this has to be something like this. That's what you are seeing here. So this circle you are seeing, you see, this is passing through pole as well as zenith. This is called meridian. Understood? Okay?
We had two different grades of it.
What?
One passing to chemical and not celestial.
No, I am connecting them. You have North Pole here, heaven chain is there. See, you can connect these 2 points anyway, from random. But the condition I am telling and that these should be greater. This means the plane should pass through diameter. So now you have only one plane in this way. Got it? Okay? It's not that difficult. Now there is something called celestial equator. What is this? So you presume that Earth, this Earth is at the center of that sphere. Sphere could be something like this thing. Fine. So what is celestial equator? Celestial equator is the projection of Earth's equator on the celestial sphere. So what I mean, this is Earth. Okay. And this is the rotation axis of Earth. You know that Earth is tilted some angle. How many angle? Fine. So Earth is rotating like this. So Earth's equator is like this is the equator will be like equator line will be like this. You just expand this to the grid sun. This is sphere, celestial sphere. It will intersect this one big circle that I am calling as celestial equator. Simple. Means Earth's equator just expanding the reaching up to the celestial sphere. So whatever the intersection will be, that is the celestial equator. समझ आ गया आपको? ठीक है? Now this is something called celestial ecliptic. The projection of Earth's orbit on the celestial sphere. So just hold on for a moment. I have mentioned the word ecliptic. You know, sun is somewhere over here. Okay. So Earth is rotating on its own axis, and it is also orbiting around the sun. Okay. So in other words, since we are on Earth, so what we will see that sun is orbiting us, isn't it? So the path followed by the sun is called ecliptic. So basically, you understood. In this case, this will be something like whatever this path we follow, which is shown here by this horizontal circle. Because that's what is the plane, isn't it? So this is called ecliptic. And now you expand this plane to the celestial sphere, you will see that is called celestial ecliptic. Now there is something called equinox. Equinox, what is this? तो तुम्हें पढ़ा ना? चलो ठीक दोबारा पढ़ा. No problem. Fine. When you start feeling boring, I will tell you some story. The instant when the sun is at the celestial equator. This means equinox is the time when the sun is at the intersection of celestial equator and celestial eclipse. This is the position. This is the time when the day and length of the day and night will be equal. Because you understand when the sun will be somewhere over here, day will be longer for south pole, shorter for north pole. Because Earth's axis is this. So north pole people will see lesser time on the sun. They will not see sunlight for long. And that's why you to the pole, it's a 6-month day and 6-month night. Understand? Now there is called solstice. Solstice is the instant when the sun reverses its north-south annual motion, defining either the longest or shortest night of the year. So the meaning of this is that you know that Earth is rotating on its axis, but at the same time it is preceding also. But I think this does not have with anything to do with the precision. This has something to do with just the motion of the sun. You see, when we are orbiting in such a fashion, sun is say below celestial equator here. So you see, what you will see that nights are longer in northern hemisphere and night will be shorter in the southern hemisphere. It will be summer in southern hemisphere, winter in northern hemisphere. But when sun reaches here somewhere over here, when your celestial equator is lower, you understand day will be longer in northern hemisphere, summer. Okay, and it will be winter in southern hemisphere. So the instant when this time, like as the sun is moving, say for example I am at rest, sun is moving. Okay, so as far as the sun will be say in this side, but since the most sun is slowly it is moving. Okay, so the length of the day will keep changing. Fine. So what will happen in the sun? In this case, as the time passes, say from December to January, February, March, April, slowly the length of the day or length of the night in northern hemisphere will start slowly increasing. And after June, it will slowly start decreasing again. So the moment when the length of the day is rather, see, till June the length of the day was increasing and then it starts decreasing. Up to 21st of December, probably. 21st of December. Fine. And after 21st of December, the length of the day will start increasing again. So these two instants are called solstices. Okay. So that this entire this you can use this concept to understand how weather pattern, why winter happens, why summer happens. Fine. Okay, let us go to coordinate systems. I will quickly go through it. But I will spend less time on the equatorial coordinate system, but I will still rest of them. So first of them are called horizontal coordinate system. Fine. This is a celestial coordinate system that uses the observer's local horizon as the fundamental plane to define two angles, altitude and azimuth. Suppose this is the observer. So when you suppose I am the observer, so this ground plane, the plane I am seeing, this is my horizontal plane. Standing up. Expect you are standing somewhere like in middle of a very open area. You will see the plain ground surrounding. This is the horizontal plane. So in this coordinate system, we use this plane as the reference. So suppose we have any star somewhere over there, and we want to measure its position. We need two coordinates, altitude and azimuth. So what is altitude? Angle between the object and local horizon. So suppose I am the observer, and say for example that projector is the star. So I will turn towards this object and understand. Fine. Now I will draw a straight line in that direction. Fine. And then I will draw another line which goes through that object. Understood? So the angle between these two lines is called angle. So because my horizon will be set in that direction. And then what is the angle with respect to that horizon? Okay? Azimuth, angle of the object around the horizon. So this I told you. Now I am telling you that in this plane, horizontal plane, I will use some point as 0. Some point. You can choose anywhere. Fine. So what is the angle of this horizon with respect to this 0? This I am telling at azimuth. So you can pick any object somewhere random. So all you need this angle and this angle. Okay? You understood this logic? Now, as a convention, what we can do, they usually measure azimuth eastward from the north point. So suppose you are here. So for you, suppose say for example, say this is my north, this is my south, this is say east west somewhere. This is my north. So I am telling this is my 0. And if I go east, that will be my, I am going from 0 to I am increasing. You understand, you can have 0, 90, 180, 270 and 360. So if I am going from north towards east, I am telling my angle is, my azimuth is increasing. But this is just a convention. You can use other ways. Okay? And the other obvious thing is that you know that objects above the horizon will have a positive altitude and objects below the horizon will have negative altitude. What will be the maximum value of altitude? 90 what? Degree. It's very important to say that Okay, unit 90 हाथी नहीं. Answer is random. Okay, fine. See, sometimes also measured from the south and increasing westward. Basically it's catching the ear from the other side. Then same way. I will say no, my south is 0, 0, and then I will go westward. So rather than starting and going this, I will say I start and go this. That is the meaning is. अब हम आगे horizontal coordinate system. All these things have practical implications. Briefly, I will touch those things also. Okay, and this horizontal coordinate system is also called the alt-azimuth system. So you have heard about the alt-azimuth mounting of telescopes. कहाँ सुना? Where? कहीं नहीं सुना. Now you know that these telescopes have different types of mountings, horseshoe mounting, alt-azimuth mounting, etc., etc. So the telescope which is built on the principle of alt-azimuth mounting follows this coordinate system. Okay, I recall somebody was explaining on the whiteboard. I don't know where, here or maybe at GMRT, that if you use one coordinate system, you can make the telescope more compact compared to the other, like in the horseshoe mounting, where you need a bigger base, etc., to cover all the angles. Okay, so here the point is that suppose you have a base of the telescope which can rotate horizontally, and the telescope can move like this. Fine. Next is the equatorial coordinate system. So you understand in this coordinate system, what we do, we use celestial equator as the fundamental plane. In the horizontal coordinate system, my local horizon was my reference plane. In this case, you understand, because celestial equator will be may have some angle. Like in this photo, I showed you this green color circle is basically the celestial equator. Okay, and again you need to define two angles. Okay, concept is same. You define some reference point 0, 0, and then angle along the celestial equator, and then from there you go towards the object. So this angle along the celestial equator, this is called right ascension. Okay, and the angle along the great circle you go toward the object, this is called declination. Okay, so who will tell me that whether the small Magellanic cloud has positive declination or negative declination? अब पहले ये नहीं बोला कि small Magellanic cloud क्या है? Can you see? Have you ever seen small Magellanic cloud from your? No, why? Because it is in the southern hemisphere, so it will have a negative declination. Okay. Before we move on, let me finish this slide. Then I will if I am not forget. So you understood right ascension is measured eastward from there, not there, the vernal point. Vernal point is this point where the ecliptic and celestial equator intersects. Basically, that is when the day and night length. So from there you go eastward. That will be your right ascension and the declination.
So there will be two such points.
Yeah. So I should north, and then that will be. You can choose anyone. You go eastward from one. Yes. Declination measured perpendicular from the celestial equator. Everybody understood? So very trivial thing. Vernal point is one of the intersections of the celestial equator with the ecliptic. What is ecliptic? I told you the path traced by the annual motion of the sun in the sky. ठीक है? अच्छा. You must have seen the star trails and all. ठीक है? So if you see the star trails wherever you are, you will not find that these star. If you can take a long exposure, you will not see that all the circles that it follows or circular arcs, they are not reaching to your zenith. The circle happens somewhere at some angle. That is your celestial pole. Okay? So that gives you an idea that you are not lying on celestial equator. Isn't it? If you directly go to the north poles, north celestial pole, you will see that it will be on just on top of your head. Okay. So you see, typically we measure this right ascension in degrees, 10 degree, 20 degree, 360 degree. So the point I want you to understand, I'm sure people must have told you, that our Earth rotates on its own axis 24 hours, and it rotates all the time. But my point is that the time period of one rotation is 24. So in 24 hours, it is the right ascension that it is covering is 360 degree, isn't it? और celestial equator का definition तो यही हुआ ना, the plane on which like Earth rotates on its own axis. So in 24 hours, our Earth rotates 360 degree. So in 1 hour, 15 degree. So you understood the conversion formula. If I tell you the right ascension in degree, you can convert this to hour. Similarly, you can go down to minutes and second also. It is not that arc minute and arc second. Okay? Here 1 hour corresponds to 15 degree. You can when 60 minutes corresponds to 15 degree. So you can determine 1 minute corresponds to how many degrees, and similarly 1 second corresponds to how many degrees. So this means you can express right ascension also in hour, minute, second. Okay. So some of you I was talking about, like I showed you in Simba you give the name of some source, and you will see RA has 3 values, some 0, 3, 5, 6, 23.5, and the declination will have some value like this. So this 0, 3, 5, 6, something number, this is hour, minute, second. And you know that you can write one line program to convert this into degree also. Isn't it? It's very trivial. Hour, you have to multiply with 50, you get degree. Similarly for minute, similarly for second, combined. Got it? So this is our today's in current time. This is our standard convention that the name of any astrophysical object we give by supplying its RA technology. So say for example, if my source, but not in degree, in our minute second. So suppose my source has some RA depth, so I will give its name something like you might have heard about, say J0356 plus minus 4456. J is just a convention. Just to start with some alphabet. Okay? 03 hour, 56 is minute. They are not giving second, no problem. Sometimes people do, sometimes do. And then here 44 is degree. So you understand, you can also divide, suppose your declination is 53.6, 53.665 degrees. You can just break it down to 55 degrees, this many arc minutes, this many arc seconds. Okay? So you may come across some astrophysical name SBSSJ010203.56 plus 55, 46, say 47.5. So this is hour, minute, second, degree, arc minute, arc second. This is our standard convention, and where the first name SDSS corresponds to the survey which is being used to detect that object. Here it is called slow digital size. Similarly, we have some other names TXS1433 plus 205. So 14 is the hour, 33 is minute, 205 and 20 is the degree, 5 is the first digit of the arc minute. This is the convention. Got the idea? So you understood how people use these coordinate systems to give the names of a physical object. Otherwise, in previous time, people were using this M81, M82, but there was no uniformity. So if you use this coordinate-based classification, this naming, then it is a uniform system. Okay? Fine. The third is the ecliptic coordinate system. So in this case, what is happening? A celestial coordinate system that uses the ecliptic as the fundamental. So rather than celestial equator, we are using celestial ecliptic. It's the same thing, but what is changing here? Your reference frame is changing. Earlier it was horizontal frame, then we moved on to celestial equator. Now we are moving on to celestial ecliptic. Then you will ask why we are doing. If the concept is same, then why we are doing different coordinate systems? So the answer is like the same. When you have this XY coordinate system and you also have polar coordinate system. So it depends on what you want to do. for your own convenience. So suppose if I am doing some experiment or I am doing some observation where I have to take into account the motion of the sun, so I will go for the elliptic coordinate system. Okay. So I just give one example. Okay. You understood? So it depends on the kind of problem you are interested in, and that depends on that you can use the reference. Sometimes using polar coordinates make the problem solving easier. Okay. Sometimes using the linear coordinate system XYZ make the problem easier. Okay. So here also we have longitude and latitude, but here we are calling ecliptic longitude and ecliptic latitude because we are using ecliptic plane as my fundamental. So again, it is measured from that vernal point. I think these two, you asked me, there will be another point somewhere behind also. I think this is one point is called vernal point, and the other point is also called some point. Okay, so people have given it. So that is the vernal point. That is not so vernal point. Okay, so we consider from vernal point. If we move along the celestial ecliptic, okay, and you see every day you see the motion of the sun. See, that is our celestial, that is the ecliptic. Fine. So with respect to us, our celestial ecliptic is like rotating, tilting. But you see, in the winter, sun becomes southern and southern. This is just because of our movement. And as the summer approaches, sun appears more and higher in the sky. Basically, our position with respect to on this elliptical orbit changes. Nothing else happens. Just because of this summer and winter. You see, the universe is so cold. Just little bit of motion in the space brings severe winter. How cold the universe is. It should go in the space. Okay, this I have told you, you know everything. So you know that ecliptic is inclined to the celestial equator 23 degrees somewhere, so I know that you are well aware of it. The axial tilt of the Earth with respect to its orbit. Fine. This coordinate system is usually adopted to study solar system objects. This I have told you that whenever you have to take into account the sun, the motion of this. Okay. So suppose if you want to study some asteroid belt object, or if I am preparing to put my robot somewhere on the Mars, I will be mostly dealing with the ecliptic coordinate system. You could use equatorial coordinate system also, no problem. But your calculation will become extremely complex. Okay. In fact, I'm sure there will be some conversion formulas also that if you know the coordinates in one reference, one system, you can always convert that into another system. Okay.
So is there something like in the RADEX system, the RADEX coordinates of any star at a particular like one same year or something won't change in different
changes. It changes.
Like it changes after a long period of
time. So you know what he was asking that suppose we have a star and we measured its RADEX using equatorial coordinate system. But since our Earth itself is moving, you know that this period, this Earth's precision, this period is I think like some 23,500 years, something like that. This is one motion. Mutation is happening, I'm not even talking. So the point that the overall sense is that the position of the star with respect to us will change over a period of time. So this means today the star which is today our not this pole star will not remain pole star forever. Because our own axis is changing after some time. So some other star will become pole star. Okay? So in astronomy, what we usually do, typically on a short time scale, means of the order of decades, this change is very negligible. So what in astronomy people do? They have people know correction factors. They can know how, because we know Earth's motion and all, we know very well now. So once in a 50 year, we change this our reference system. If you go to symbol or if you go to NED and you search for any object, you will find its coordinate mentioned in the J2000. And you may also find the coordinate in J or say B1950. Every 50 years, we update this system. You see, this order changes like order of few arc second to few arc minutes, not more than that. But some changes there. Where suppose you are doing some observation, few arc minutes, it's a good number. Instead of observing Andromeda, you may start observing. People who have not even opened NED, they will not be knowing what I'm talking. But people who have opened it, they will be knowing. You go to NED, you simply write MED7. Like I showed you good pictures of MED7. So you should have tried checking out what we know about MED7. Why it has beautiful jet. There are coordinates for the jet sun. Okay. And the people who are familiar with the DS9, you move your cursor along the image, you see the coordinates are changing. And you see the change in very, very time. Okay? So, fine.
So in this coordinate system, does the like any coordinate for a solar system object stay fixed for like one particular time? Like as in, when you talk about the equatorial coordinates, it's useful because it will stay fixed to the star compared to the all-time coordinates. So is this also something similar to that where we stay fixed for the solar system object?
Yeah, yes. Well, yeah. You see, yeah, that's what you discussed. That's why. Okay, let's go to galactic coordinate system. So you know in galactic coordinate system, what is this? This is a celestial coordinate system that uses the galactic plane as the fundamental plane to define two angles, galactic longitude and galactic latitude. This is a picture of our galaxy. This is real Prof. Taken in the, and this image is shown in the galactic coordinates. This means galactic center will be at 0, 0. If you can go on top of our galaxy, I will show you. This is the galactic center. Sun is somewhere over here. Okay. So first of all, you understood you are talking about the galactic plane. Fine. So what is galactic longitude? Measures eastward along the galactic equator. So suppose you join the line from the sun to galactic center. This is my reference plane, reference line. Galactic center somewhere over there. See, Earth is tiny compared to the size of solar system. So basically, if I say the sun represents the entire solar system, there is not too much. Okay, you can understand that our entire solar system somewhere there only. So basically, that's why we are using sun as the reference. So just connect. Suppose we have the sun to galactic center. This is my 0, 0 line, one axis, and you have some object, some galaxy somewhere. Fine. So you move along the galactic plane from this 0, 0. This will give me galactic longitude. समझ में आया ना बात? ऐसे ही मान लो ना कि मान लो galactic, suppose the galactic center is somewhere over there, and this is galactic plane, like a horizontal coordinate system. Okay, and you have some object that watch. This is the galactic longitude, and you understand? This will be your galactic latitude. B. समझ में आया ना? Basically, that is an infrared sky, infrared image. You can see this dust lanes and all. The real photo. I think it's I don't know. It's probably stranger. Fine. Galactic latitude also I told you that this measures the angle above or below the galactic plane. So you understood that galactic plane is very dense for us because lots of dust, star forming region, giant molecular clouds, etc. Everything like galaxy is like our Milky Way is like a disk. Okay, so thick disk, bit thick. Compared to its length, this disk is very small, but it's a bit thick. So along the disk, the density of matter is too high. Okay, so you have to understand. Suppose our galactic center is somewhere, some direction, and you are looking towards it. But you understand there will be quasars, other galaxies behind also. They may not be visible in optical wavelength because the light coming through the galaxy will be obscured by dust. Fine. So whenever, so this means the confusion of whether there is a source at that position or not is higher if the object is lying in the galactic plane. I am telling galactic plane, say 5 degree above and 5 degree below from my 0, 0. This plus minus 10 degree region, I am telling this is a very dense region where the confusion of and finding an extragalactic source is very high. I am telling you what is the example of that. Like how we use this coordinates. Okay, so say like whenever I'm looking for any quasar in gamma rays, etc. So usually we say that we have selected objects above 10 degree, below 10 degree of the galactic plane to avoid source confusion. Because our own galaxy has lots of star forming regions. Star forming regions means what? There are lots of gas and material. Okay, and you have heard the word something called cosmic rays. These are the extremely energetic particles whose origin we do not know. One of the possible origins people have proposed is the supernova remnants. With supernova is where the particles gain energy because of the shock. These cosmic rays are very energetic particles. Mostly they are protons. Okay, but they could be more proton and other ions. So when this cosmic rays are passing through this dense interstellar medium, okay, so they will interact with the medium and they will lose some of its energy, producing a glow. This is called diffuse gamma rays. So rather than detecting gamma rays coming from a point sources, like you see this rod is like a point source. Suppose you fill some like fog here, so you will see light is like a foggy structure. This fog is gamma, diffuse gamma. There is no point source, diffuse gamma rays. All these branches like people study. So this problem is more in the galactic plane. When I will teach you gamma ray astronomy, I will show you the real gamma ray picture of our galactic. How it looks like. It will not be that beautiful as you are seeing here. Okay. So that's why if you go above and below the galactic plane, far from the galactic plane, your possibility of confusion is less. Got it? Na? Okay. Now let us talk briefly about something called sidereal time. ये सुना है? तो पढ़ा दिया ना? अच्छा बात. ठीक है ना? क्या करेगा? Okay, what is sidereal? The time scale that is based on Earth's rate of rotation measures relative to fixed stars. Since you have already figured it, I will ask question. Okay, so the point is that this is a time scale that is based on Earth's rate of rotation measures relative to fixed stars. So you know that if you look at the night sky, the position of a star will not change. It will look like that today our North Pole star will remain tomorrow also that same position. It will not go some more there. Fine. So see, using this concept only in the like previous day in the stone age, people were measuring the time. So they measured, okay. Then later came sundial and all those things came. But before they were measuring stars only, na. Suppose you are traveling in Pacific, suppose you are floating in Pacific Ocean. Like thousand kilometers only water, absolutely nothing else. You want to read? I have a very good book about it. There's one person, I think he is Dutch or someone, and he traveled along full Earth. Like he took the whole round of one Earth from a boat, and he wrote a book. I have the PDF of some Joshua. So I was reading that book and I was trying to visualize what it is amazing. The point I want to tell you that suppose you are somewhere nowhere. There is no watch. Okay, no internet. Then how will you know the time? So the sailors in the old days, what sailors will do? They will use the stars, etc., to measure the time and determine the direction where they are going. Where to go? No one is north side, north, south, left, right. You don't know. Okay. Another, when you are in the Pacific, you are close to equator. So the weather will also not change drastically. Means there will not be severe winter and there will not be severe summer. It will remain more or less summer. The position like Sri Lanka and like that. So in that location. So you can so the position of sun will also not change drastically in the sky. It will be more or less template all the time. You cannot use the sun also. So people will using these stars. That's where this concept of sidereal time, etc. came. Fine. So one sidereal day equals to the time taken to return to the same position with respect to distant stars. So today I saw pole star at some time, and after some time, again I saw the pole star at the same position. So this time duration I am telling as a one sidereal day. Fine. Okay. Next. Viewed from the same location, a star seen at one position in the sky will be seen at the same position on another night at the same sidereal time. This is what I just repeated. What I told. Fine? Anu? You understood? Good. So on Earth, one sidereal day is approximately 86,164 seconds. Now you can do it. You can do this experiment. Isn't it? You can do it. What's the big deal? Now you see, this concept is based on Earth's rotation on its own axis. Because this way 24 hours it is taking. I'm telling 24 hours, it is 86 points. But you know that this is slightly less than 24 hours. Okay?
सर लाइक अगर मैं आज एक सेम पोजीशन पे किसी स्टार को देखूंगी और मैं कल उसी पोजीशन पे उसी स्टार को देखूंगी तो अलग दिखाई देगा सेम पोजीशन
because the stars are so distant, okay, their position with respect to us will not change because whatever you are telling, it is correct. Earth itself is rotating, moving along some axis around the sun. So Earth's own axis will slightly move, but the stars are so distant, their position will remain both at the same. It is like, suppose, say for example, I give one simple example. You look at this projector from here, okay, and after 24 hours, suppose you reach there. So the position of the projector will change with respect to the background. Why? Because it is very nearby. Understood? Suppose if the object is way too far, it is something to do with your angle with which you are see. If I draw is okay. Suppose this is the object. Fine. Today you were here, and tomorrow you reach here. So today you saw the position of the star, and you have something in the background. There are stars. So you can measure the position of your source with respect to background. Fine. And after 24 hours, suppose you reach here, and you again observe. So the position of the star with respect to background will change. Suppose say for example, there is a bright star here. Okay? This is a bright star. Bluish, blue star, hot star, so bright star. Suppose you are observing from here. So you will see that my star, the distance between the target I am interested and the distance between this star, this separation is something. And tomorrow if you reach here and you are observing from here, so you will see the distance between my star and that bright star has changed. This means you will feel that star has moved.
But उसी same position से measure करूँ तो कैसा feel?
Baba, उसी position means I am telling that your whole earth is itself will be.
I am not changing my position. I am standing there only. Like I measure a distance of star from here, and on the next time again measuring the distance from there only.
Yes.
So that will change now.
What will change?
The position of star.
So Baba, that's what I am telling you. Ideally, it will change, but the question is how much it will change. This is our telling. How much it will change. So this will be increased. That's why. Because in cosmological scales, the motion of Earth is tiny compared to the distance of stars with us. So in one day, you are at the same position, but your base itself has moved. Your Earth has only moved one day. It will somewhere over there. The Earth is orbiting in an elliptical orbit around the sun. So see, what I am simply telling that you observe the star at some point of time at a certain location. Fine. After 24 hours, you again look at the star.
On the same time.
On the same location and on the same location at the same position. So if the instrument, suppose you have to measure that distance, etc., is super duper accurate, you will find that the star position has slightly changed. Why? Because Earth is moving. Again, because the Earth is moving.
So which coordinate system are
Hold on. Okay? But the question is that the distance that Earth will move in one day is negligible compared to the distance of those stars to the Earth. It is something like that when train is moving. So what you see? So the objects which are like adjacent to the train, they appear moving faster, or the object which is like some tree somewhere over far, that looks move faster. Why? Because of this. थोड़ा सा समझ में आया ना थोड़ा? Since the objects which are nearer, a little bit of change in the position, we will find it. But if the object is super far, because I told you that like the entire universe is expanding. So the galaxy which you are the distance you are measuring, suppose some redshift or etc. we take, okay, their redshift itself will be changing, but our distance with those galaxies is so huge that their own motion is not going to make any measurable change. That's why we do not change it. We cannot say today in 2005 the redshift was 0.5 and in 2021 the redshift became 0.6. Doesn't happen. Because 0.5 to 0.6 if you change, so the distance of the star will change by 1 billion years. That is it. Got it? Okay? Let me go to that. Hopefully the next picture will clear you out. Okay, now there is something called solar time. Solar time is also similar like sidereal time, but it is based on the sun. So rather than observing the star, suppose if I measure the time when sun is at certain location, and after some time, then I see when the sun is at the same location again. So this time period is called one solar day. Okay, so here you see what is happening in this case. Distant star you see there, you see the sun, the earth. You see the first photo. In first photo at 12 o'clock, say noon, the star and the sun both are at the same position. Fine. Now, next day, if I look at the same star, this. So see, when you look at the star from here, you will see this is a star. After some time, you look at the star again. So since the star is so far, the star will appear at the same time. But since the sun is nearer, sun will not reach at the center by that. Sun will reach to the center after slightly some more time. Because the sun is very close to us compared to the distance of the star. So this difference is of the order of 4. Okay, this difference is of the order of 4 units. So when we have a reference system based on the stars, we have a sidereal day. When we have a reference frame based on the position of the sun, we have a solar day, and the difference is of the order of 4 units. And this difference is only because the distance of the sun with respect to us is much smaller compared to the distance of the star with respect to us. So that's why within one day our motion will show a slight difference in the position of the sun. ज़्यादा पढ़ूंगा तो कंफ्यूज होगा तो आगे चलो फिनिश. Okay, now this is called our angle. Alright, right. The angle, first of all, it is an angle. So there are usually two planes. If it is an angle, so you need two planes. So the angle between two planes, one containing Earth's axis and zenith, which is meridian. Okay? And the other containing Earth's axis and a given point of interest. So, suppose you are interested at this position here. Okay? You are an observer here. Okay? So what I am telling, and say for example, my zenith will be somewhere over here. Okay? If I draw a meridian plane, the meridian plane was the plane which passes through zenith and north pole, south pole also. Yes. Okay? So this plane you understood? This bluish color plane. Okay? This is my meridian plane. So I have one. Now I want to know the angle of, say, our angle of certain object. So what I have to do, I need one more plane. So what that plane will be? you draw a plane in such a manner, it also passes through the same axis. Because this is the celestial pole is the axis around which our Earth rotates. Okay? So my source is there, my celestial pole is this, so this plane. So basically you can say it's like connecting a plane with your point of interest with the north pole. So one plane is this, one plane is this, so this angle is between, this is called our angle. And if I understand correctly, yeah, this is a convention that if you go west of meridian plane, west means suppose this direction is west, so you say it's a positive, or you say it's a negative, or you can use geometry. And I think this is very similar to what we call is hour of righteousness. Probably it is, but I'm not very sure. It may not be. All right. And no, it is a think it during lunchtime. Okay, you see, can be expressed in degrees or in time, 24 hours, 360 degrees. If you think it comes to this. Twilight. Movies of videos में देखा होगा सर, है ना? है ना? Twilight Saga. I haven't. All right. What is the twilight? Twilight is the time between the day and night when there is probably some light, but probably some not some. Probably means it is neither day nor night. Okay. Twilight is the time period when you cannot say it's night and you can also not say it's day. In a common language. Formally, we say it is the time between the day and night when there is light outside, but the sun is below the horizon. अच्छा क्वेश्चन आता है कि sun is already below the horizon, then how the light is? Scattering of? Don't scatter the sun. Scatter the sunlight. Twilight occurs because Earth's upper atmosphere scatters and reflects sunlight, which illuminates the lower atmosphere. See, because you imagine like our Earth is like this. Okay? So, say for example, this is our Earth. We are observer somewhere over there. Suppose the sun is here, below the horizon. You understood? This is the horizon. So sunlight will go and it will reflect. Lower sun will go from higher layers. The reflection will happen. Okay? This everyone understood? Morning twilight is often called dawn, and evening dawn is also called dusk. What I'm teaching. I know you will ask why I'm teaching you this. Coming to that. This was very important golden day when people were traveling without GPS. All these things were useful. In today's time also I will tell you one example. You know that there are three stages of twilight. पढ़ लिया है? किसने पढ़ा है? नहीं पढ़ा है? तो surprise है ना? Surprise phase. Twilight also has 3 phases. Yes, there are 3 phases of twilight. Okay, किसको पता है? तुमको पता है? मत बताओ. Don't tell me. First is called civil twilight. Okay, so civil twilight occurs when the sun is less than 6 degrees below the horizon. Okay, suppose your horizon plane is this, sun is 6 degrees below, up to 6 degrees below the horizon. We say it is civil twilight. In the morning, civil twilight begins when the sun is 6 degrees below the horizon and ends at sunrise. Sunrise, when sunrise happens, the sun is just coming above the horizon. So 6 degrees below to up to sunrise. This period is called the morning twilight. Same thing you can understand for the sunset also. Okay? Means like when the sun just went below the horizon and by the time it reaches 6 degrees below the horizon, this period is called evening twilight. In civil twilight in evening. You know that several countries use this definition of civil twilight to make laws related to aviation, hunting, and the usage of headlights and street lamps. You might have noticed in the evening on the street lights, they are switched on at certain time, and in the morning they switched off at certain time. I do not know how it happens here and now, but the principle is this. Okay, we will say that's why it's not civil twilight. We will say the sunlight, this lights, street lights will be switched off when the civil twilight starts. Because you know that just after civil twilight, when it starts, then there is enough light. So you do not need street lights. So you need a reference point to switch on and switch off street light. Na? Though like usually nowadays people do not do that. They simply keep it on all the time. You might have seen it. I have seen it. And you might have seen street lamp. There are 24 out there. 24 hours will twilight. No problem. Okay? Then there is something called nautical twilight. It is again same concept, but when the sun is between 6 degrees and 12 degrees below the horizon. So you understand, after sunset, first civil twilight will come, and then you will have nautical twilight. And as the name suggests, this was used, and you understand in this time, the light will be less bright compared to civil twilight because sun has gone further down. Okay, and this was people were using the stars, but in this case, the stars and the horizon is visible during the nautical twilight. Means you can still see the stars will start. You will start seeing the stars. Okay, but before that, the sunlight was so bright, you may not be seeing. You are not seeing the star. But when the nautical twilight happens, then we start seeing the star. That's why the time when your street lamp should be on. This is mostly used by sailors. That's why it's named nautical twilight. You should read books about sailors, and recently one song also came. I think it's called "There Was a Ship That Was Put to Sea." Good. Okay. Now finally got astronomical twilight. This is what we use. This is used by astronomers. Astronomical twilight occurs when the geometric center of the sun is between 12 degree and 18 degree below the horizon. You are further gone down. Okay, so this you understood. Before this time, the sky is absolute black. This means after sunset, when the sun goes below 18 degree, then we say night has started. And when night will end, when the sun will come just above 18 degree from the horizon. You understand when astronomers start observations? When astronomical twilight. Okay? See, that's how we do it. That's why all these definitions are there. Okay, and this you understand, astronomical dusk is the time when the sun is just coming above 18 degree. So after this time, the sky is no longer illuminated. Fine. If I show you one photo, yeah, so this I have already told you. See, this is exactly what I was talking. You have the sun. Suppose this is like from night to day, sunrise. So we have night, then we have astronomical dawn, nautical dawn, civil dawn, our dawn. Okay? Thank you. Okay? I will first take up the questions from the online participants. So Prakash, you will check if anyone has any questions.
Sure, Vijay.
In between, you people have any questions? Please ask. If you have no questions, go for lunch.
So the sidereal time you're talking about, since it's 23 hours or 6 minutes around that time, so can you say that the stars rise 4 minutes later every day?
No question? No question? Lunch break. Go, please, people do. I'm just waiting for if there is a question from now.
So you said that there are coins. So how do you?
So because now we have well advanced information about the coordinate systems and all. So whenever a satellite is designed, suppose the instrument is designed, such as CCD etc. is designed, whenever they observe some part of the sky, so whatever the data shows, that data also contains the positional information of that data. So suppose if you see a standard jet, okay, so that we know that okay, this different parts of the jet, what is the corresponding position, because that we are able to detect it.
So there is no one particular.
And you understand, this is true for nearby, so where we can resolve. For the distant object, we cannot resolve them. So they all look like jet, quasar, Indian, gold, they look like one point. If you can think of it like the angle, suppose you want to resolve something, means you want to suppose resolve means what? Suppose this pencil. Okay? You resolve means you can see this end as well as this end separately. So what this angle, this pencil is making with respect to your line? This angle. How small you can measure, that defines your meaning. Here, since the object is very close, you can resolve this, you can see. But if I bring it farther and farther, the solution will look like a one point. Why? Because its angle is got it now? That's the concept. Fine? Hold on, just one second. I have not had any questions from online participants.
Yeah, there are no questions.
So no problem. So thank you everyone for joining. Okay, and then I will stop sharing the screen and I request to stop the live stream. Thank you.